Okay, so let's move on to our next topic, which will be the center of mass. So up to now, we have generally treated forces as if they were acting on point particles, right? We may have called them blocks, we may have called them hockey pucks or whatever else, but we pretty much just treated them as a particle, ignoring their shape and their size. Now we're going to actually start considering real shapes and sizes of things, real extent. Uh, and we find that we can treat these extended bodies like things that have shapes still as point particles if we assume the forces are directed in line with the center of mass. And in fact, that's kind of just what we've been doing without explicitly saying so, right? We've just been assuming that that when a force comes along and hits a circular hockey puck, that it hits it um, in line with the center, right? And in the cases of basic geometric shapes, the center of mass is generally close to the center of the actual shape. What we'll find, okay, sorry, we already said that. And the center of mass is defined as the point in space around which the mass of the object is evenly distributed, right? So in the case of a circle or a square, right, it's pretty clear it's going to be right at the center of that circle or square. For a triangle, it's a little less intuitive because there's a little less mass up near the tip than at the base. And so it turns out that the center of mass is actually, if you draw these three intersections between in the triangle, the meeting point gives you the center of mass, right? And it turns out to be, in this case, because of the nice tall triangle, a little bit closer to the base than to the tip. But we can extend this idea to more irregular shapes if we know how to find the center of mass in a way that's less geometrical and more mathematical. Then we can go ahead and start to handle very odd, irregular shapes. To the limit where you can take something like this parlor trick where people sometimes balance two forks on a toothpick and can balance it on a wine glass, right? Even going to the extent of burning away the end until it reaches the point of contact and you get this magical looking thing. But it's really that if you do the mathematics, if you add up all the mass and give it the right weights, the center of mass of this odd configuration of two interlinked forks is actually right there. And so what you're doing is you're really supporting this, this odd configuration at its center of mass, and so things hold up and balance properly. So let's take a look at the mathematics of how to determine the center of mass of a irregularly shaped object. But let's start with how do we find the center of mass of a regularly shaped object? We can view, the trick is that we can view an extended object as just a collection of particles, right? I mean, in reality, that's what we are, right? Our bodies, everything else is just made up of cells, and the cells are made up of smaller molecules, and molecules are made up of atoms, and the atoms are made up of point particles like protons and neutrons and electrons, as you've learned in chemistry. So it's perfectly legitimate to view this extended object as a collection of particles. The position of the center of mass of an object is just the mass-weighted average position of each particle in that object, right? So the average position would just be taking all the positions and adding them up, right? But what we do is we know that some particles are heavier than others, have more mass than others, and so we give those particles a little more weight. The way this is done mathematically is by taking not just the sum of all the x positions, right? Like if we had a bunch of points along the x-axis, to find the average position, you just add up all the positions and divide by the number of things that you had. A weighted average, in this case a mass-weighted average, is done by taking the mass of each particle times the position of each particle, summing all those up, right? Taking that product and summing up all those products, and then dividing by the total mass of all the particles in the system. Okay, we would do the same thing in the y dimension and in the z dimension, and you get the center of mass, the x coordinate of the center of mass, the y coordinate of the center of mass, and the z coordinate of the center of mass. In this notation, m sub I is the mass of each of the is the ith particle, mass of the ith particle, right? And there's n of them. And the coordinates are the xi, yi, zi give the position of that particle, and m is the total mass when you add up all of those n particles together. Instead of writing in terms of x, y, and z, we of course can write it in terms of some simple r vector, a position vector, in which case we would just write it as a sum of the mass times the position vector pointing to that mass, sum all those guys up, and then divide that by the total mass, right? Where the position vector is just x times the I position vector, j times the j hat, z times k hat. And this we studied back in chapter 1, right, in the vector notation, where we had unit vectors. Okay. In the textbook, you'll see this written sometimes as an integral, right? And for real continuous objects, like a continuous rod, where we're not really talking about a bunch of particles stuck together, at least not pictorially, right? Then we take this to the limit of the particles being infinitesimally small, like we talked about protons and neutrons or whatever. And for any real object, we can really get the center of mass by taking not the sum, but the integral of the position of each little element of mass, right? So there's a little bit of, we break it up into little tiny slices, right? Where dm is basically a little infinitesimal slice of mass, right? So if we had a rod and we would kind of take that rod and break it into tiny little slices, and each one of those slices would have some amount of mass, and it would have a position for that little slice, an x position for that slice, and we would add all those up in integral form. Right? And again, we can alternatively write this as the integral of the r vector times the slice of mass that this r vector points to. Okay, so let's take some concrete examples. We can now legitimately deal with forces on real extended physical bodies by treating the forces as if they act directly on that center of mass of the body. What we're saying is that Newton's second law for extended bodies is that a net force applied to a mass will cause an acceleration of the center of mass of that body, right? So we're being just a little bit more explicit. In the past, we just said the acceleration of the body, right? What we're saying now is that the net force on the body, F, on an extended body with total mass, what's going to accelerate is that point at the center of that center of mass of that body, right? And the rest of the body will come with it if it's a rigid body, right? But what we're implicitly saying by stating it this way is that we're assuming that the forces act only on the center of mass, right? We are directing now our forces towards that point that we've located at this somewhere inside, typically inside the body, that is the center of mass, and we're pretending that the forces act directly at that point. And by assuming that, we're excluding the possibility of rotation. And we've done this kind of implicitly many times throughout the quarter. We've said, we push on the block, but we push on it in a way that doesn't cause rotation. So what we're really saying when we say that is we're applying the force in line or directly onto the center of mass. And then it is the center of mass that we think of as accelerating. And then we take a step back and say, well, the center of mass moves forward, the rest of the body moves forward with it. Okay, so let's take a look at some concrete examples. Imagine a system that's a discrete system, not a continuous system yet. It's just that consists of 3 different particles of 3 different masses, right? Mass 1 is located at -1 plus 1. Mass 2 is located at -1 minus 1. And mass 3 is located at coordinate +2 plus 1. Mass 1 is 10 kilograms, mass 2 is 20 kilograms, and mass 3 is 30 kilograms. Our goal is to calculate the center of mass of this entire system, right? So we've seen that the formula for calculating the center of mass is to take the mass weighted average. In other words, take the mass times the position of the particle, sum those all up, and then divide by the total mass of the system. Right? In this case, we're going to do it for the x and the y components independently to figure out where the x and y components coordinates of the center of mass are. So let's start with the x. We're going to take 1 over the total mass. The total mass is 10 plus 20 plus 30 kilograms. And we're going to multiply that fraction by the sum of these products, right? The mass times position of the product. So the first mass is at an x coordinate of -1 meter. The second mass, 20 kilograms, is also at -1 meters in x. And the third mass is 30 kilograms, and it is at an x coordinate of +2 meters. Right, so that gives us -10, -20, +60. So that's -30 plus 60, so that's going to be 30. 30 over a total of 60 kilograms is going to give us about half a meter, or exactly half a meter. So the x coordinate of the center of mass is at +0.5 meters in x. The y coordinate for this system is going to be the same formula, but we're going to take the y coordinate in the product now. So we have, again, 1 over 10 plus 20 plus 30, which totals 60 kilograms. This time times 10 kilograms plus +1 meter in the y, 20 kilograms for M2 times -1 meter, and +30 kilograms for M3 times the fact that it is +1 in the y direction. Right, so when we add these up, that is a +10, that's a -20, which together that's going to make a -10, and add another 30, and that's 20. 20 out of 60 is a third, or 0.33 meters, and so we now have our y coordinate for this system of three masses, the center of mass of these things, and it turns out to be right here. Okay. Let's now take a case for a more continuous system. This is a little bit more mathematically involved, and we of course would never ask you to derive something like this on an exam, but you can see that the point of doing this is to show that mathematically we get the intuitive result, which is that if we ask you to calculate the center of mass of a uniform square block that's a centimeter wide, you can kind of guess it's going to be in the center of the cube. Right? This is a cube, 1 centimeter by 1 centimeter, 1 centimeter. One should expect that the center of mass should be at exactly 1/2, 1/2, 1/2. So let's find out if that turns out to be the case using the formulas we gave for a more continuous distribution. So the solution here is to divide up the cube into thin slices, right? And we can do this in many ways, but let's start by trying to get the x coordinate of the center of mass, in which case we're going to take a bunch of slices that differ in their x position, right? So we're going to slice these things up into kind of YZ slices that each have a different x position. And then we can divide that block, by dividing the block into a bunch of thin slices, each slice has a volume that is the total width, right? Because this is W, so that's a square, and it's going to have a thickness of delta x, right? So I'm going to take one slice here, delta x, another delta x, another delta x, another delta x, cut up into tiny little slices, and each of those slices it will have a mass, which we'll just say that's a delta m, right? It's given by delta m. What is delta m? Delta m is going to be the density of this material, right? And we haven't really talked about density a lot yet, but density is just defined as the total mass divided by the total volume, right? So you take the total mass of the block, divide by the full volume, which is 1 by 1 by 1, and you get a density, a mass per unit volume. We're going to take that density and we're just going to multiply by the volume of the little slice, and that will tell us how much mass we have in that little slice, right? That makes sense. But that little slice had a volume of W by delta x, or W squared times delta x, right? So that little incremental amount of mass that I add by adding that little slice on is rho, the density, times the width squared times the thickness of that little delta x. Or if we take this to a limit of cutting this up very, very, very finely, we have infinitesimally thin slices where instead of writing it as delta m, we write it as dm, right? A little differential slice in mass is equal to rho dv instead of delta v, which is equal to rho w squared dx instead of delta x, right? So now what we can do is we can take the integral of all these slices together, but we take a weighted integral, right? We take the integral weighted by the mass of each slice, and then we divide by the total mass to give us the center of mass, right? But now what we have is we have dm is equal to this whole thing, right? Rho w squared dx. But rho and w squared are just fixed quantities. One's the density of the material, the other is the width of the material. Those aren't going to change. And so we pull that outside the integral, and we have rho w squared over m times the integral of from 0 out to the full width of this cube of x dx, right? Where we've pulled the dx down here and pulled this stuff up front. Okay, but the integral of x dx is just 1/2 x squared, and evaluated the two endpoints, which gives us a w squared over 2, right? Which gives me a rho v over m. Because if I pull one of the w's from this w squared and pull it up here, then I have a w down left over here, and I have a w cubed. The w cubed is the volume of the cube, right? So I have rho times the volume of the cube divided by m, but rho times v is just equal to m. Right? So this is just 1, so I'm just left with w over 2. So that is a quick derivation of the fact that the center of mass in the x direction is exactly at the halfway point of this cube in x. Now we could repeat this whole process by taking y slices or z slices, and you get the same answer, and you would find that the center of mass is at exactly w over 2 in both x, y, and z, right, as expected. Okay, so this is a kind of a quick 5-minute derivation, maybe more like 10 minutes, derivation of the fact that when we can have a uniform block of material, right, then the center of mass is really just at the center of that block, right? And so for all intents and purposes, we can replace the entire volume of mass with all of that mass being concentrated at that one point. So now if we move on to another example where we're not doing a derivation, but asking specifically, if I have two uniform blocks, one here pink on the left, green on the right, and we glue them together. But now it's not uniform. The two blocks are made of different materials, so that each block is a centimeter by a centimeter by a centimeter, but the red block has a mass of 3 kilograms, while the green block of the same size only has a mass of 1 kilogram. So you can think of this as being basically made of a steel block, and this is something like a little plastic block. Now we want to calculate the center of mass of this composite material, this now rectangle that is glued by combining two blocks. What is the center of mass of this composite block, composite rectangle? All right, so our solution is that we've previously found, in just the last slide, that the center of mass of each uniform square lies at the center of that square, of that cube, right? So the center of mass for the red block is at exactly minus 0.5 in x, plus 0.5 in y, plus 0.5 in z. The center of mass for the green cube is at plus 0.5 in x, plus 5, plus 0.5, plus 0.5 in y and z. And what we can do is we can attribute the full mass of each block to its representative center of mass. And then what we can do is we can find the center of mass of the glued double block by the same process we did in the previous example, where I just gave you the coordinate of a mass and a coordinate of a mass. And we assumed all the mass was concentrated there, but here we can also assume that all of the mass of the red block is concentrated at minus 0.5, 0.5, 0.5, and all of the mass of the green block is concentrated at this coordinate, plus 5, plus 0.5, plus 0.5, plus 0.5, plus 0.5. So then we just go back and add them discretely like we did before, and the center of mass for the x coordinate is 1 over the total mass of the system plus the sum of these mass-weighted average positions, right? And so plugging in numbers, total mass is 3 plus 1 kilograms. The individual blocks are 3 kilograms at 0.5 x coordinate, 3 kilograms at minus 0.5 centimeters, plus 1 kilogram for the green block, times plus 0.5 centimeters for its x-coordinate, which when we throw that all into a calculator, we get exactly 1/4 centimeter, minus 1/4 centimeter, so that the x-coordinate of this, the center of mass of this composite block lies at minus 0.25 centimeters in the x direction. And in the y direction, you can see just from symmetry that that the total, sorry, we can see from symmetry that the center of mass is going to still be at 0.5 and 0.5, but you can do this process for y and z and verify that yourself. As a final topic, let me show you one reason that we brought in the idea of center mass here as opposed to bringing it in when we start looking at rotations where it's going to be equally important. Where one of the nice things about the center of mass is that if all the mass of the system can be viewed as operating from the center of mass, right? Then we can take, just like we did here, we can take two or more particles of different masses and treat the combined mass as all being located at the coordinate of the center of mass. So now if we look at this example we've had previously, these two sticky buns coming together, colliding and moving off on a frictionless surface, we can revisit this and look at it in terms of center of mass. Right? So this time, what we're going to do is we're going to assume that the masses are equal, just to make life a little easier. But to keep it interesting, we're going to make them have different velocities. The eastbound block, this one, is going to be moving at 1 meter per second, which is exactly half that of the northbound block. So the block that's moving straight up, or straight north, is got 2 meters per second of velocity. All right. So when they meet at the origin, they're going to combine, they're going to move off at some angle. We can analyze this in terms, just like we did before, look at the total initial momentum in x, the total initial momentum in y, right? And again, because of the way we set this up, the total x is just the momentum of mass 1, total y is just the momentum of mass 2. Now, just as before, because momentum is conserved, the x component of momentum is conserved, and the y component of momentum is conserved. So afterwards, the combined block must have a momentum in the x component, in the x direction, that is just equal to what it was initially, which is just m1v1. And the final momentum in the y direction, that of the combined block, has to equal to the total momentum in the y direction, which was just m2v2. So the combined block is going to have a momentum of m2v2. We can then solve for the velocity in x by taking the combined momentum, which we just figured out is just m1v1, and divide by m combined, which is just m1 plus m2. Right? Do the same thing for y. And if we plug in numbers, we get m1, 1 kilogram, times v1, 1 millimeter per second, divided by the combined mass of m1 plus m2, which is 2 kilograms, and we get 0.5 meters per second in the x direction. And in the y direction, we do the same math, and we get 1 meter per second. So the combined mass is moving faster in the y than it is in the x, which makes sense because the mass of the block that was moving in the y direction was moving faster in the initial condition. All right, so now what we're going to do is we're going to revisit this in terms of center of mass. So let's take those blocks and work them backwards from the collision. Right, this one was moving at only 1 meter per second. So 1 second in the past it was here, 2 seconds in the past it was here, 3 seconds in the past before the collision it was there. In the y direction, the block 2, which was moving at 2 meters per second, 1 second before the collision, it's down here at -2. 2 seconds before the collision is down here. 3 seconds before the collision is down here at -6. After they combine, they collide and they stick together. They move forward, moving up 1 meter per second, while only moving to the right by 0.5. So it's got 0.5 and 1. At the next step in time, it's going to be 1 and 2, then 1.5 and 3, and so on. Okay? But what you can do now is we can look at this is the center of mass of the system once it's stuck together is pretty clear. It's just the center of these two blocks, right? What is the center of mass of the system before they got stuck together? Well, now we've got two masses that are separated, but we know how to deal with that, right? We take the coordinates of this mass and we take the coordinates of this mass and we add them together in the weighted sense. But because these are equal, right? These are basically two equal masses, we can almost do it by intuition. We can say center of mass is obviously along here, but when they're separated, what we can do is we can kind of take the line between them, right? Imagine that they were two, like a big dumbbell where you have two weights on either end of a long pole. Well, where would the balancing point be? It would be at the center of the pole if these two masses are the same, right? At the time before, when they were even further apart, it would just be two equal masses on the end of an even longer pole, but the balancing point, the center of mass, is going to again be the center of that pole, right? Same thing out here. Longer pole yet, center of mass is going to be the center. But if you look, lo and behold, if you trace this back, the velocity of the center of mass before the collision is exactly the same as the velocity of the center of mass after the collision. And that has to be because if we take the system to be completely isolated, right? This is a frictionless surface, it's ice. There's no other forces coming in. The only forces acting were between these two masses, this mass and this mass, right? So if there's no external forces, then there's nothing bringing momentum into the system or out of the system. So the center of mass, which was moving like this, after it collides, the collision didn't bring in any external force. It didn't bring in a third party that came in. It would only involve the internal things, the two things that were internal to the system to start with. So without any external forces, without any external um, uh, anything acting on it, the momentum of the system, of this isolated system, is conserved. This thing had a momentum that was bringing it along this way, so it has to continue along that way. The momentum of the center of mass has to be conserved. All right, and I think that ties it up.